Now we're gonna move to another function called finv. It's almost the same. It's type of f distributions and it's inverse cumulative distribution function. This is abbreviated from finv. I choose to get everything that are related to each other in the statistical perspective, so it's very helpful like if you're taking math class or having like data or working in a company that you're gonna use most of this all of those like equation. And this in this episode I will be very big in telling you guys what's the important of every function, because this how we're gonna be engaged in like learning those function. And when you know the importance of anything, you're gonna be more capable to learn it more with like more passion, more engagement and enthusiasm. So FNV, it's inverse cumulative distribution function. And as I said, why we do care about this function right now? Okay, it's help us in finding critical values in f-test, which is essential in function like ANOVA, and we're gonna explain ANOVA later today. And help us in also regression analysis. This is one of the analysis for statistics used in hypothesis testing and like maybe finding the confidence intervals. Confidence intervals like measures or like tells you how your data is accurate, and like if you are taking math class I think you're gonna understand me more. And finally like statistical simulation and modeling. So if you are making simulation for your data or like using different form of modeling, for sure you're gonna use the FNV. Okay, so right now it does need three things. Okay, it does need probability value. Okay, and it will be given to you for the most cases, but we're gonna find it or like we're gonna put a value for it for us now. And 2 degrees of freedom, degrees of freedom of numerator and degrees of freedom of denominator. So we have two instead of one, and just like the difference between T and V and F and V. So let's see an example. So right now B equal line space. We explained this several times by now. 0.995 and 100%. Okay, so quick recap. It starts as 0.005, end at 0.995. There is 100 evenly spaced points between them. So 100 evenly spaced point between this number, the start point and the end point, and this my line space. Okay, this is, as I said, 2 degrees of freedom, right? The first one, let's make it 8, and let's explain this to be the numerator. The second one, let's make it 9, and let's explain this to be the denominator. This might be given or you have to find them by yourself, so it depends on instructor type of question, depend on like the nature of your class. Okay, so this FNV has P, and as I said, 2 degrees of freedom, number of degree of freedom, right? So df1, df2. So both are having the blue shade, then like both are relevant or like matching, connecting to each other, then like I am good to go. Okay, but before doing this, let's clear the workspace. So clearing the workspace because I don't wanna think like to overrun on each other. Like if I have to df1, then like MATLAB will get like confused and error might happen. So right now if I press run, so I got a column with 100 double as like the line space. As I said, it was 100 evenly spaced with the 2 degrees of freedom. Okay, this might not obvious, so I wanna plot this. I wanna show these numbers in a plot because it's gonna like give more representation for my like code. So let's plot this using the P and X, F. So P is my probability values and F is my F inverse cumulative. So right now I will make just the usual things about my like plot, like grid on x label, let's make it like b, y label, f and v. Let's make like something like title. We explain this in depth, like how we can make our plot polished, but for your guys' time right now, I'm just make this to help us like explain to us or like guide us through the graph, but this is not the goal today. Okay. Semicolon, semicolon, semicolon. So right now it gives me the plot. So now it gives me a better representation. So from 0 to 0.9, okay, the plot is increasing. And then from just 0.9 to 1, it start taking a horizontal or start going through like equilibrium. Okay, and this is just from 0.9 to 1. So the behavior from 0 to 0.9 is just like increasing, we can say like exponentially little bit, but from 0.9 to 1 you start to take a sudden huge increase on the x-axis. On the y-axis, the same thing, like it start increasing from 0 to 2, from p when p is 0 to 0.1, but we can see from 0.9 to 1 it increased on the y-axis from 2 to 7. So that's why I'm saying like it's very hard to understand this just in front of you as numbers, but when you put this in front of the plot or like in front of figure in front of you, of course you're gonna be like different experience.